Today we have optimization, which is basically application problems for finding maximums and minimums. So we're going to be told to optimize something, meaning can we find the maximum output or can we find the minimum output? So when you see the word optimize, that just means find a maximum or minimum. So we're gonna optimize the area, we're gonna optimize perimeter, we're gonna optimize cost, revenue, profit. So all of those mean are let's find a max or minimum. Okay, so to get us set up to understand optimization, we're going to look at a geometry problem. We're going to look at this problem with rectangles. So example 1 says, find the dimensions of a rectangle with an area of 200 square feet that has the minimum perimeter. So our job here is to minimize the perimeter. So we want to minimize the perimeter. Okay, so let's look at everything they're giving us. They say, find the dimensions of a rectangle with an area of 200 square feet. All right, well, here's my rectangle. And I'll just label X as the width, height is Y. And one thing we have to know are the actual formulas or equations that we're working with. So for a rectangle, first off, we know that area is length times width, or in this case, it's going to be X times Y. This is the area of a rectangle. And then the other thing we need to know, we have to minimize the perimeter. Well, the perimeter of a rectangle is 2 times the length plus 2 times the width. Okay. And it's our job to minimize the perimeter. Okay. But before we do so, we have to make a substitution with the information they're giving us already. They're saying that the dimensions of a rectangle have an area of 200 square feet. So we know that our area is 200 square feet. So I'll put that in here. Area is 200 square feet. Well, just so happens that the formula for area is X times Y. And I'll show you in a second why we make a substitution. But here we're going to make a substitution for Y. And again, I'll tell you why in a moment. So since area is X times Y, we get XY equals 200. And in order to get rid of this Y in the perimeter equation, well, we're going to make an equation for it. So all we're going to do is solve this area equation for Y, which means I'm going to divide it by X. And Y now equals 200 over X. Okay. And this is our substitution. It's going in for that Y. All right. So now I'm going to show you why we are making a substitution. So take our perimeter equation. And if I said to optimize it to find a max or min, well, remember the process for finding a maximum or a minimum. To find a max or min, you take the first derivative, you set it equal, and you solve for X. So if we did that here, if I said, come on, this pen doesn't want to write. There we go. If I said d over dx of everything, then I would get p prime equal to 2 plus 2y prime. Now, this is our issue, the y prime. There is no need for a y prime in this equation. If we have a y prime, this means that we now have a related rates question and the rectangle is changing at a certain rate, which in this problem, it is not. So whenever you deal with maximums and minimums, your max and min isn't constantly changing. So there's no need for a y prime. This is why we make a substitution to get rid of that y. And we put the perimeter equation all in terms of x. So I guess keep it simple. We don't need y prime, so we make a substitution to put our equation all in terms of x. Okay, so what we're going to do is plug in that substitution. So we're going to get p equals 2x plus 2 times my new y value of 200 over x. And now this equation is all in terms of x on the right side. So we just have to clean it up. P equals 2x plus, you'll get 400 over x. Okay. And now since this is all in terms of x, we can now take the derivative of it because it's all in terms of one variable. But before I do so, I'm going to rewrite it as 2x plus 400 x to the negative 1. I just take that x and I flip it to the numerator. Now we take the derivative with respect to x on both sides, and we will get p prime equal to 2 minus 400 times x to the negative 2. So what we have done is we put the equation all in terms of x, and now we're optimizing. We're finding a maximum or we're finding a minimum. So we take the derivative, and now we're going to set it equal to 0, and we're going to solve for x, just like we did for the max and minimum problems. All right. So now take p prime, set it equal to 0, which means you get 200 minus 400 x to the negative 2 equal to 0. Solve for x. I'm going to add 400x to the negative 2 to the right side. I'll get 2 equals positive 400 x to the negative 2. The next thing I'm going to do is take that x to the negative 2 and flip it back to the denominator. So we'll get 2 equals 400 over x squared. And now we're actually solving for x. So this means I have to take this x squared and multiply it to the left side. So this means we now have 2x squared equal to 400. If we divide by 2, we'll get x squared equals 200. And now we just square root both sides. Oh, my calculator's over here. And now square root both sides. And you get the square root of 200, which will give me x equals plus or minus 10 square root of 2, or 14.14. And remember, since we're dealing with length, we can't take a negative measure. So our answer here is going to be x is 14.14 feet. So this would be considered our critical number. This is where a maximum or a minimum is going to happen. So all we're going to do now with this critical number is find the value of y. Because all this question says is find the dimensions that would minimize this perimeter. Well, now we know that x is 14.14, which means if we want to find the dimensions, we need to find y. So we're going to take this x value and plug it back into our substitution, which says y equals 200 over x. So that's our next one. So then I'll just do a different color. Let's see. We're going to have y equals 200 over 14.14, and 200 over 14.14 happens to be also 14.14 feet. So to minimize the perimeter of a rectangle with an area of 200 square feet, to minimize the perimeter, the dimensions of X must be 14 by 14.14 feet, and the dimensions of Y must be 14.14 feet. This means we no longer have a rectangle. What do we have?
Square.
A square. So the dimensions that would minimize the perimeter are 14.14 feet by 14.14 feet. So if you optimize a rectangle, we get a square. All right. So that's how optimization works. Any questions on that process? Okay. Let's try another one. So these are just warming us up for actual word problems. So 2, find the dimensions of a rectangle with a perimeter of 148 feet and has the maximum area. So that means we are now going to maximize the area. We're going to optimize the area. But let's draw our pictures again. Here's my rectangle. Here's X, here's Y. And the formulas associated with the rectangle, we know our area is X times Y, and our perimeter is 2X plus 2Y. Okay. Here we need to maximize the area. So this is the equation we need to maximize. But once again, we have to get rid of that Y. So this is what we're maximizing. My pen would write. Maximize. Okay. So this means, once again, we're going to have to make a substitution with the given information. This says that the rectangle has a perimeter of 148 feet. So let's call this step 1. We'll say sub. We know that the perimeter is 148 feet. Set that equal to 2x plus 2y. And now solve this equation for y, so we can plug it into the area equation for y. So that means that 2x is coming to the left. I get 148 minus 2x equal to 2y. And then I'll divide everything by 2. And this will give me 148 divided by 2, that's 74 minus x equal to y. Here is our substitution. And now we're plugging it in for this y. So that's next. 2. Plug y into area. So we're going to get A equals x times y, which is the blue, 74 minus x. So that's our new y value, 74 minus x. Distribute the x, and you'll get 74x minus x squared. So once again, we have an equation all in terms of one variable. This is all in terms of x, which means now we take the derivative with respect to x on both sides, and we'll get a prime equal to 74 minus 2x. And now, after you take the derivative, you set it equal to 0, and you solve for x. We'll call that 3. Set a prime equal to 0. So 74 minus 2x equal to 0. Move the 2x over to the right side and divide by 2. You'll get 37 equals x. And I think we're still in feet. Okay. So once again, this question says, find the dimensions that will maximize the area. So if x is 37 feet, we need to find y to complete our dimensions. So all we have to do is, once again, take our value of x and plug it into our substitution for x. So that's what we're going to do here. We're going to say 4 plug x into, what should I just say? Yeah, let's say plug x into y sub. How's that? So you'll get 74 minus 37 equal to y. And 74 minus 37 is 37 feet. So again, we optimize a rectangle. This time we maximize the area. So to maximize the area, the value of x, the length of x has to be 37 feet, and the length of y has to be 37 feet. So again, we get another square. Why does this happen with rectangles? Well, 1, it most likely depends on the problem, but 2, nobody likes rectangles. It's better to hang out in a square. Your room is a square, your classroom's a square. The only thing that's a rectangle is a hallway. Logic right there, guys.
Squares are optimal.
There you go. All right. So, any questions on that example? So this is just showing you how optimization works. So we're going to be given some information. We're going to put that together. We're going to optimize it, which means when I say optimize, we're going to take the derivative. We're going to set it equal. We're going to set it equal to 0. We're going to solve for x and go from there. Okay. All right. Now, there we go. Example 3, an actual word problem. Okay. An office supply company sells X permanent markers per year. The yearly price demand equation for these markers is P equals 10 minus 0.001X. The total annual cost of manufacturing X permanent markers for the office supply company is C of X equals 5,000 plus 2X. A, what price should the company charge for the markers, and how many markers should be produced to maximize the yearly revenue? What is the maximum yearly revenue? So our job in example A, or part A, is to maximize the revenue function. So that's what we're saying right here. We're going to maximize the revenue function. And once we maximize it, which means we optimize it, take the derivative, set equal to 0, whatever value we get for X, we're going to plug it into the price equation given, and we're going to plug it into the revenue equation, which means we don't have a revenue equation, but we know how to create one. So remember, revenue is always given, red and blue. Revenue is always given by the equation R of X equals X times P. R of X equals X times P. Well, lucky for us, they give us an equation for P. Hey, look, that's a sub. We're making a substitution, just like we did in the last two. We plug this in for P, which means we get X times 10 minus 0.001X. And now distribute the X, and we get 10X minus 0.001X squared. Here is our revenue function. And now, since we have the revenue function, we're going to maximize it, which means, you know what that means. You're going to take the derivative and set it equal to 0 and solve for X. I'll just say maximize. We'll get R prime. And that'll give me 10 minus 0.002x. We take our prime, set it equal to 0. We get 10 minus 0.002x equal to 0. Add the 0.002 over to the right side and divide by 0.02. And that becomes 5,000. So we get 5,000 equal to X. So what this means, if we look back at the problem, is that remember that X represents the amount of permanent markers. So X is our critical number that we find from the first derivative. So this means that since we're maximizing this problem, at 5,000 markers, we're going to have a maximum revenue, and we're going to know the price to sell these markers at, because that's what it's looking for. What price should the company charge for the markers, and how many should be produced to maximize yearly revenue? So this is one of our answers. In order to produce maximum yearly revenue, we need to make 5,000 markers. Okay, now what we're going to do with this is take this 5,000, plug it into the revenue function. That'll give us the maximum yearly revenue. And then we're going to plug it into the price equation, because that price equation is the equation for how much these markers should be sold at. So we're going to plug it into both of those. Okay. So I can do that over here. We'll say plug X into R of X and P. So I will do R of X first. Sure. We'll have R of 5,000, and that'll give me 10 times 5,000 minus 0.001 times 5,000 squared. And let's see what that gives me. And if we make 5,000 markers per year, our yearly revenue is going to be 25,000. So this is the maximum yearly revenue. Okay. And now we need to know what price to sell them at. So here comes P. And I'll get 10 minus 0.001 times 5,000. I'm pretty sure that that's $5 per marker, but I'll check it. And we'll get 5. So in order to make a yearly revenue of $25,000, we must sell these markers at $5 a piece. It's a pretty expensive marker. Okay, any questions on that process? It doesn't seem so bad once you get all the equations down. Everything else is repetitive from there, because it was what we were doing with the graphs. To find a maximum or a minimum, you take the equation, you take the derivative, set it equal to 0, solve for x, and then plug it in where you need to. Okay. Let me make sure I got everything. What price? How many markers? Maximum yearly revenue. Yep, we got all three. Okay. B, what price should the company charge for the markers, and how many markers should be produced to maximize the annual profit? What is the maximum annual profit? Okay. So our job is to maximize the profit function. We don't have a profit function, but once again, we know how to make one. Remember that profit is given by revenue minus cost. We created a revenue function on the last problem, and they gave us a cost function in the original paragraph. So we're going to plug those in. Let me keep that up there. Revenue is 10x minus 0.001x squared minus, and remember, whenever you plug in the cost function, always put it in parentheses, because that negative outside has to distribute. Okay, now let's find profit. Maybe I could write that smaller. Let's see. Hey, there we go. Okay, distribute that negative. 10x minus 0.001x squared minus 5,000 minus 2x. Combine like terms. And I'm going to write it with the highest power first. That x squared comes down. And then you can put the 10x and the 2x together, which will give me 8x. And then last is that 5,000. Actually, P of x, there's our profit function. Okay, so we have profit, and now you know what to do from here. You are going to maximize it. So that means we take the derivative. Which is going to give me negative 0.002x plus 8. We set it equal to 0. And we solve for x. I'll just move that 8 over. Sure, it doesn't matter. And then divide by negative 0.002. And 8 over 0.002 gives me 4,000. And this means 4,000 markers. Okay, so in order to have a maximum profit, we need to produce 4,000 markers. Okay, so now, once again, what we're gonna do with that number is take it, plug it into the profit function, and then plug it back into that price function. And that's it. So let's see. We'll say, once again, I'll zoom in. There we go. Plug X into P of X, and P, I'll say price, so we don't get those confused. Okay, so first up, since it's to my left, let's plug it into that profit function. It's going to be P of 4,000 equals negative 0.01 times 4,000 squared plus 8 times 4,000 minus 5,000. Okay. So let's see, negative 0.001 times 4,000 squared plus 8 times 4,000 minus 5,000. We get $11,000. And this is the maximum yearly profit. That's take-home money. So that's after all costs have been taken away, you give to share $11,000 with everybody. Woo, good stuff. Marker business. Okay, last we plug into that price equation. P equals 10 minus 0.001x. So for that, I'll just say price, and you get 10 minus 0.001 times 4,000, and I'm assuming that's $6. That's price per marker. Okay. And that's it. That's optimization part 1. We have more optimization on Wednesday, but any questions on this?
In part A, it says to maximize revenue, you make 5,000 markers, but maximizing revenue doesn't necessarily mean maximizing profit. So you actually want to make less and charge more.
Exactly, because, well, remember that revenue isn't take-home money.
Right.
So
revenue is just what you made from the sales.
Exactly, it's what you made from the sales. And then remember, profit puts the cost equation into effect. So now you're doing your revenue minus your cost, and we're only walking away with $11,000. So if this were to ask for what is the cost of producing this many 4,000 markers, well, you have your max revenue of 25,000, your max profit of 11. This means it costs $14,000 to make those markers.
Cool, thank you.
Yes, sir. All right. Well, we are done.